Good afternoon. We go ahead and get started now. Good afternoon, everybody. Welcome to the Eastern Branch monthly meeting. I'm Brad Smith. I'm the president-elect. Ned is out today. We have a great turnout today. Thanks everyone for coming. We have a very interesting presentation today on the I-26 Green River Bridge. But first, I've got a couple of quick announcements from the Eastern Branch. So we do have our 29th annual Eastern Branch Golf Tournament scheduled. That's scheduled for Monday, November 3rd at 12 Oaks Golf Course right down the road in Holly Springs. You'll get an email about that in the next few weeks. So that should be a great event that supports our scholarship fund. We also have an upcoming Eastern Branch Younger Members Group social. That's a Durham Bulls game that's going to be on July 26th. If you're interested in that, tickets are $10 and sign up ends on July 11th. If you would like to sign up, then check out the email that's sent out by the Younger Members Group, or if you're not on that email list, get in touch with me or Josh Rosenthal, and we'll get you where you need to go. The last event coming up is a construction site safety summit that NC State is hosting. It's not associated with ASCE, but they've asked if anyone from ASCE would be willing to represent at this forum. It's a one-day forum that's on the subject of how to better prepare engineering undergrad students in the area of construction site safety. That'll be on Wednesday, September 17th. So if you have any interest in being on the panel, or if you want to just join as a participant, then let me know and I'll get you in contact with the organizers. So that's all the announcements for now. I'll go ahead and introduce you to John Sloan and Tim Sherrill. They're going to present on the I-26 Green River Bridge Rehab Project. Very interesting project. John has served as AECOM's North Carolina Bridge Program Manager with AECOM since 2016 after joining the firm in 2004. And Tim is the NCDOT Preservation and Repair Engineer with the Structures Management Unit. Been working with NCDOT since 2001 after spending 12 years in the consulting engineering world. So thank you, John and Tim. Over to you.
Sure. Good afternoon, everybody. I appreciate the opportunity to kind of jump in and start this presentation. It's really John's presentation, and he's been kind enough to allow me to kind of introduce the project. Again, Tim Sherrill, North Carolina DOT. So let's get started. So the Green River bridges are located in Henderson County, just south of Hendersonville, North Carolina, on I-26, about 30 miles south of Asheville. It's a very important route for us. Obviously, a lot of folks, just tourists, are driving in to visit the mountains, or maybe folks that are up that way take I-26 down to Charleston for vacation, what have you. And also in Charleston, the southern terminus of the I-26 is there's a large port there in Charleston. So there's a lot of trucking that comes up from there through Western North Carolina to hit I-40 or to go farther north on into Tennessee. So a very important route for us to keep in a good level of service. This picture you see here is looking north. The roadway is actually labeled east and west, but it really is kind of oriented north and south. But we're looking north here at the bridge, 2 lanes in each direction, about 20,000 cars per day on both bridges. Very steep downhill grades on both approaches to the bridges, and also some sharp horizontal curves there as well. Whoops, sorry. Some sharp horizontal curves there as well. The Eastern Continental Divide is in the distance there on that ridge, and the Green River obviously flows underneath these bridges to the Atlantic. The Green River game lands surround the area, lots of hiking, kayaking. It's a very popular outdoor area and very environmentally sensitive. as you drive across the bridge, like most bridges, you don't really think about what you're driving across. But these bridges are especially unusual for us anyway. If you look over here, you can see there's a person standing here with a hard hat and safety vest on. That's John. And John is 6'6" tall. And look how tall these girders are. These girders are 14 feet tall. And, you know, it's kind of, again, you don't realize how big these girders are. It's really impressive. They were designed to be non-composite. And let's see, the approach spans are simple spans, total 5-span bridge. The approach spans are simple spans and a 3-span continuous in the middle. Here's a typical section of the two bridges together. The clear roadway width on both bridges is 28 feet. The spacing of the main girders is 24 feet between each, the main girders. It's a deck, a stringer, floor beam, and main beam system with 2 main beams for each bridge. And so it is a fracture critical condition. And it's 30 feet between each of the bridges. There are transverse stiffeners at each cross fane where the floor beams are located. It's 23 feet 7 inches spacing for those. The bridge was built in 1968. There was some significant rehab and repair work done in the 90s, and John will get into that a little bit more in just a few minutes. And I don't know if you can see here, you can see on the upper left here, the splice plate, the bolted field splice, not unusual there, but on either side of that, you see there are some bolts in the web of the girders. That is a little bit unusual, but that is related back to some of the rehab, and John will touch on that was done in the 90s. Oh, also, there's longitudinal stiffeners in the compression zones. Here's an aerial view of the bridge. Again, 5 spans, 100-foot simple spans on each end, and then the 3-span continuous in the middle there. The total length of the bridge is 1,050 feet. And it's about 230 feet off the water. Here's a view from the catwalk below. It is in the top 5 of highest bridges in the eastern part of the United States that is on the interstate system. A few more little bit of information. The bottom flange of these girders is 3 3/4 inch thick, and 30 inches wide, and the web is 5/8 inch thick. The interior hammerhead vents, they are actually they're concrete, reinforced concrete, and the steel that you see here is really a stay-in-place form. And I think the steel stay-in-place forms were probably used for a couple of reasons. One reason is it's probably more aesthetically pleasing in the area, an environmentally sensitive area, outdoors place like this. Just that brown rust color is a little bit more aesthetically pleasing for the area. Plus, we're in a big gorge here. So if you have these forms in place, for the columns and what have you, removing those forms is going to be a lot of work, right? So it made sense just to leave those there. So I'm going to hand this over to John here in just a moment. You know, we started looking at doing some rehab preservation on this bridge starting in about 2016, 2017. And the two bridges overall weren't in terrible shape. The substructure was good. The superstructure had some issues with it that we knew we could address. The worst items were the bridge deck. As a matter of fact, as John was developing the project, a hole developed in one location in one of the bridge decks. That's how bad it was. And so we were trying to figure out the scope of work to do and what we could get done. Again, a lot of traffic in there, very narrow. And so to do any deck work, we're going to have to close lanes or close a lane at a time. And the division was very reluctant to do that, and understandably so, a lot of traffic through there. And so we were back and forth, just trying to come up with ideas of how to handle this, and a little bit of a wit's end. And I remember after a project call, John called me one day and he said, Tim, you might think I'm crazy, but I think the approach on this is to join these two bridges together, common deck, what have you. And thought about it for just a minute, and I said, John, you are right. I think you're crazy. And, but as engineers, a lot of times, most of the time we like to do comfortable things, right? We often try to stay within our boxes and do the easy thing. And that's great. It's typically a conservative thing to do. And we know what we're doing is easy to kind of get done. But sometimes on projects like this and other challenging projects, maybe you sometimes do have to do things that are a little bit crazy. So I'll pass it on to John.
Thank you, Tim. Yeah, I'm John Sloan with AECOM. I manage the bridge group in North Carolina. So yeah, as Tim mentioned, we've been working together on this project for 7 or 8 years now, something like that. So here's the outline for the rest of the presentation. We'll go through the history of the bridge, feasibility study, load testing, final design, and then construction and instrumentation. So as far as the history of the bridge, the bridges, they were built as separate bridges in 1968. Catwalks were added underneath to improve access for inspection in 1976. They added guardrail in front of the barriers in 1984. Then 1992-93 timeframe, some cracks were discovered in some of the steel elements. So a major rehabilitation was conducted then with a bunch of testing. 2012, there was an expansion joint replacement. And then in 2017, 2018 timeframe, we started looking at what we should do. NCDOT was evaluating what it should do with these bridges. Here's a picture of the guardrail in front of the barrier that was placed in 1984. This is a view underneath of the structure. So you can see basically the catwalks. You can see the K-frame diaphragms that are there, some X bracing. I'm going to talk about those in more detail in a minute. And then right here by the girders, you see these cover plates that were installed in 1992 and 93 as part of the rehabilitation. So here's a close-up of the cover plate that's bolted to the bottom flange. And then you see as well the gusset plate where these cross frame members frame into the girders. We're going to talk about in those in detail as well, because there were some issues related to those. So in 1992, some cracks were discovered in one of the girders, and that prompted a very in-depth, detailed investigation that NCDOT conducted. They hired Lehigh University to conduct an assessment. The investigation was focused on one area in particular at the beginning, span D, girder 1. And so at the bottom flange, they took several cores. They completed hardness testing, chemical composition testing. They noted that one of the plates in the bottom flange did not meet the material specifications of the original construction project. Okay, so there was high carbon content in one of these plates, and that's what led to the cracking when the bottom flange was welded to the web. And you can see the crack there in the photo in the upper right. You can see the list of cores that they took here. On the left were the principal investigators for Lehigh University. And I need to make a note about the project team as well. So some of the names you saw on the front slide, Ed Zoe and Mark Guzda, they helped us out with this project. They're not here today, but they're going to present with us in a few weeks at the International Bridge Conference. So they're heavy hitters, and we're a critical part of this project team. Ed Zoe got his master's degree and his PhD at Lehigh University in the 1980s, and he studied under these men, John Fisher and Ben Yen. So he knows them personally. He was not at Lehigh while they did this project, but he's a national expert in steel and instrumentation, and he was a technical expert for us on this project. So here's a plan view of the web in this area. There were 3 cores that were taken, again, where there was some cracking, and then this one crack here in particular, they drilled an arrest hole. This is a schematic of one of the cracks in the flange. You can see there where you have the fillet welds to connect the web to the bottom flange. All the cracks related to hydrogen-related cold cracking at fabrication. So these cracks, all the cracks that were discovered in this area were present in the bridge from the time it was fabricated. Probably happened immediately after the welds took place, within a couple of days after the welding. There's no indication that any of the cracks actually grew in the 24 years between the time the bridge was fabricated and the initial discovery of the cracks. There was patina that had developed inside of the cracks, so on and so forth. So that's basically a rundown of the cracking in those areas. So what they decided to do as a rehabilitation was to add the cover plates. And there's another picture. It does terminate at when you transition from the positive moment region to the negative moment region, but even though only a single plate was defective, they bolted these cover plates to the bottom flange in all spans, on all girders, both bridges, just for redundancy and to strengthen the structure. The way they did that at the bolted field splices was that they bolted these tubes onto either side of the splice and then had a post-tensioning rod to post-tension it. They removed the bottom flange splice plate and then put the cover plate on and rebolted the splice plate back together. So another issue that they ran into in 1993 was these gusset plates and the members that frame into these gusset plates. So they're very slender. And they were getting some distortion-related fatigue cracking along the welds of this plate. So NCDOT has over 500 pages of non-destructive testing. They did magnetic particle testing, ultrasonic testing, and liquid penetrant testing that was completed between July and December of 1992. So they did a thorough investigation, were able to eliminate all of these cracks, mainly just by grinding them out. But the reason that these cracks were occurring, the NCDOT with Wisjan and Elsener did some load testing, and this is an instrumentation gauge, strain gauge that is attached to the cross bracing. You see the large hump there. That's when the truck or a vehicle goes across the bridge. But then you see all these secondary oscillations in the data. And so what was happening is a truck goes across the bridge, but then the bridge continues to vibrate. Okay. And so you have this very slender cross bracing that's going up and down the whole time. And that's a problem for the bridge. So they added these posts that frame in to the superstructure and connect down to the X bracing. That stiffens the system. And so that X bracing is now no longer flopping up and down as vehicles drive across the bridge. They also bolted these angles to the gusset plates and the stiffener to just, again, stiffen this whole system together. So that brings us to the feasibility study. And initially, we were thinking there would just be a conventional rehabilitation, but we decided to take a step back and say, maybe we need to look at different alternatives for this crossing here. So we looked at no build, conventional rehab, tie the bridges together, create a single bridge, and then replace the bridge. As Tim mentioned, as we were doing the feasibility study, a huge hole opened up in the concrete deck. That's a picture of the repair that was completed. So again, if you're going to do a conventional rehab with an overlay, you need a really good substrate. The original deck in the main spans, the three span continuous unit, was only 6 3/4 thick. They used lightweight concrete. It was a thin deck. So there were some concerns that a 50-year-old deck was going to hold up over the long term. So fatigue again was an issue. There were some indications that were noted in the bridge inspection report. You've got a bridge that when we looked at it and evaluated the existing bridge, we discovered that it does not meet the code for fatigue service life, or for an infinite fatigue life. And so we were basically infringing on the factor of safety. There were a few indications that were noted in the bridge inspection report. NCDOT hired S&ME to go out and do a thorough investigation with non-destructive evaluation of the indications. A lot of it was really minor. Most of it's really minor. They did discover some issues with some of the welding in terms of start and stop of weld spatter, arc strikes, cluster porosity, overlapping welds, those kinds of things. A lot of the issues that were noted in the inspection report, they were just able to grind out, and it was not a problem. Overall, after they had finished up, there were really only 5 locations that were a concern that we were able to include in the rehabilitation of the bridges. So looking at the replacement alternative, again, everything that Tim said at the beginning with the terrain makes a replacement very difficult and expensive. Certainly it's feasible, but it's just very, very expensive. You've got mountains all over the place. You've got very steep grades, difficult grades. Bringing the roadway up to modern standards would, you're raising the profile very high. It's just very expensive, and you don't want to necessarily include that in your bridge preservation program, right? You don't want 2 miles of roadway upgrades. You don't want to be using your bridge preservation funds for that kind of interstate upgrade. So this is like a half typical section of the replacement alternative. As we looked at the costs, we were looking at, the cost of replacement is over 4 times the cost of the alternative to tie the bridges together and rehabilitate them. So in the end, as we've concluded our feasibility study, NCDOT decided to move forward with tying the bridges together with floor beams and replacing the deck. As we transitioned into final design, we scheduled a load test. Mark Gusta led this effort, so he's going to be with us in a couple of weeks when we present at the International Bridge Conference. But NCDOT provided these trucks. They were about, I think they're 70,000 pounds plus or minus, so 35-ton trucks. We ran them in a lot of different configurations. We tested both bridges. We did it at night with a rolling roadblock with the state police providing that rolling closure for us. This is a view of the instrumentation. There's strain gauges there on the bottom flange. You've got a transducer that's transmitting the data wirelessly with the antenna and so on. So this is out at midspan. We've got a strain transducer on the top of the bottom flange that you see there. And then underneath, just out of view of the photo, there's another one on the bottom of the bottom flange. And those, basically the data there, we had 2 gauges to confirm that the cover plate is part of the structural system. And so we were essentially reading the same strain values on both of those gauges. So that was very good data for us and reassuring. The other gauge at the upper left by the gusset plate, that's evaluating the fatigue, right? Because this is a fatigue prone area. It's a category E fatigue detail. So that means you have a very low stress range that is allowable for that particular detail. We instrumented the cross frames. This is the K-frame diaphragm. So we've got all kinds of instrumentation there. This is the X-frame where we've got a lot of instrumentation as well. That's the actual instrumentation setup. So just as a summary, basically we confirmed that the bridge is behaving in a composite manner. We confirmed that this is really important. We confirmed there's no live load forces in the K-frames and the X-frames. Obviously, they were critical for constructability, for bracing and those things, but they're not participating in the live load resistance of the system. We validated, another really critical aspect of this was validating our design model. And we'll get more when we got into construction, there was a lot of comparison between the load testing results and the actual analytical model that we developed to make sure that what we were designing and analyzing is representative of reality. So in the girders, I'll give you some maximum stresses here. In the girders, the maximum flange stress under the live load was 2.7 KSI in tension in positive bending, and 1.3 KSI compressive stress in negative bending. And then, sorry, for fatigue, we had basically a stress range of 3.5 KSI for fatigue, which is under our 4.5 KSI limit. But once you factor it, you're basically infringing on your factor of safety. So what we did there, this is a picture from construction. I was kind of skipping ahead to construction just a little bit because this idea came from our load testing team. They said, well, hey, why don't you cut out a radius there from that gusset plate? Okay, and that the code, the bridge code, allows you to change this is now a category D fatigue detail, and it gives you a allowable stress range of 7 KSI. So that improved the performance of that detail there. Now transitioning into final design, this was our team, and this is only the structures team. I like to show this slide. There's absolutely no way we could have done this project without a really outstanding team that came together. Again, this is just the structures team. I like to show this slide because this was a multidiscipline transportation project, right? So hydroplaning was a major concern, hydraulics. There's a history of crashes under rain events in this area. So that was an issue we had to reckon with. Basically, the work zone traffic control design was very challenging. How do you shift traffic back and forth as you're constructing this deck to maintain traffic on the bridge throughout construction? That was a big challenge. And then the roadway design was also very challenging because you've got a fixed bridge and you've got to basically thread the needle with your roadway profile. Very, very difficult and challenging from a roadway design perspective. Well, this is what we ended up with for our final typical section. We put a floor beam in bay 2 to connect the two bridges together. We strengthened all 4 girders. We added cover plates. We brought the detailing up to modern code requirements. So we added stiffeners, both transverse and longitudinal stiffeners. We added these knee braces here, or corbels, whatever you want to call them. That was necessary primarily because you get really high moments in your floor beam connections as you shift traffic back and forth, and as you remove the deck and then put deck back on. There's really high moments in those connections. So we did that. And then obviously you've also got the stringers in bay 2 that were added. We welded shear studs onto the top flanges of all the existing girders and the existing stringers to make the bridge fully composite. Even though we load tested, the bridge is behaving in a composite manner, we can't assume that, right? Because of the code requirements, we have to be conservative, especially at ultimate. at the ultimate condition, if you really push this bridge out, it will probably lose that composite behavior as there's some slip between the deck and the top flange. So we bolted shear studs onto the top flanges of all the girders and stringers to make it fully composite so that we could assume that the behavior is composite. So we replaced the bridge deck with a lightweight deck and utilized a PPC overlay. So here comes the visualization. I think we should have sound here that shows basically how we got the bridge constructed and all the work that we did to pull this together. Let's see if we can do this. Here we go. All right. Didn't go quite that fast in the field. Yeah. So our visualization team did a great job on that. So this is our model, just a screenshot of one of our models. So this is basically the phase. The deck on the left is the existing deck. The deck in the middle is the new proposed deck. And then on the right, we've removed the deck. Okay, so again, that's just one stage. We had 37 stages in our construction stage model. Very, very complex, complicated model. This is nonlinear, right? So we've got to account for the stresses at each stage in the design and in construction to make sure that we're not overstressing at any given point during construction, but also we're accounting for all those changes throughout the whole construction process. In addition, we included the original construction and the 1993 retrofit in our modeling as well. There's just the next stage in the model. Again, you've got proposed deck in the middle and over here all the way to the right. And then on the left, you've removed the deck. So with this, we've got beam elements for all these cross framing members. Again, the X frames were at the piers, the K frames were kind of interior. So we had beam elements for those interior elements, and then the girders were modeled with shell elements. We also did some local modeling to confirm the behavior of the bridge at these diaphragm locations. That was very helpful for us. We had multiple different models where we looked at things in a very localized way, just to confirm the manner in which the stresses are flowing. And then, of course, we had to account for all these stresses throughout the whole construction sequence. So basically, you begin and you add the median barriers or some of the barriers. That's the initial load. Then all the iron work. We required all the steel and iron work to be done first before you actually load up the bridge. We got the girders up to code. So once we did all the iron work, the bridge met the AASHTO code. Everything we did was in accordance with the new AASHTO LRFD code once we got all that iron work in place. Then you can see we've added the deck, those 3 large stress increases. Then you remove the deck on one side. That's where we reduce a lot of stress there. And then you add the deck on back on that side. Then you remove the deck on the other side, and then you add the deck on the other side here as well. And then this last one is the PPC overlay. I think this drop is when we're removing some of the temporary barriers. And then here we're adding the PPC overlay. So we had instrumentation to record data throughout the whole construction process. So, you know, that was the previous slide was our actual analytical model, but we had instrumentation to evaluate to make sure that our model, again, is accurately representing reality. So we put instrumentation on the bridge. We've got instrumentation on the floor beams. That's the green. We've got it on the girders, that's the red, and then the blue is temperature gauges. So we have some level of understanding of the thermal fluctuations, what's going on with temperature. We've got these data loggers here where we're sending data to the cloud. And, you know, we've got all the data on the internet, online, on the cloud, so that we can access it at any given time. You know, again, the main goal here is as we're going through and changing the dead load, we're trying to make sure that we've got an accurate handle on all the dead load changes throughout construction. But the problem with that is you've only got the strain gauge can't tell the difference, right, between thermal fluctuations, daily thermal fluctuations, seasonal temperature changes, live loads, dead loads. All these different things. We've just got a strain gauge that's all it measures is one thing. It's just measuring strain. Okay, so we have to parse out all the different data, and in order to do that, to try to zero in on the dead load changes, we use what's called the Bayesian dynamic linear modeling method, and we process that data, and we utilize that to zero in on the actual dead load change. So that gives us a baseline. That's what you see on the left there in the green line. And then we added, so for example, in this case, we added a barrier. So this in the upper photo, there's no barrier. Then in the lower photo, we've added the barrier. And that's basically our baseline before and after is shown in the green shading there. So now getting close to the end of our presentation, I've got about 10 or 12 slides to just go through the construction. So this is basically a photo just when we've added the floor beams and the interior ironwork. This is a slide from below. We've got the contractor had this really nifty idea to put what's called a safe span platform underneath the bridge. You can see he suspended it. They suspended it from the bridge itself. And that allowed all their iron workers to get down and have easy access to the bridge. This is a picture of the retrofit of the knee brace or the corbel. Basically, the one on the left is the before photo. That was removed and added this larger, stronger knee brace. Again, you know, this the behavior of the bridge is dominated by the floor beams in the transverse direction. This diagonal member is not really doing a lot for you other than providing some bracing in terms of live load resistance and those kinds of things. So again, live load, you've got basically the stiff beam element and a high moment demand. So that's why we needed such a big brace there. As far as the substructure goes, we've got post tensioning that we added because you're adding some additional dead load. And so we post tension the cap to increase the moment demand. Some demands in the substructure are actually reduced because you're tying the bridges together. So if you've got a wind load on the bridge, it's now supported and shared by both bridges. So there's actually a lot of reduction in those kinds of demands. Here's a photo of the stringers added. Got the shear studs there for composite behavior. Photo of the stringers and the floor beams from below. These hangers are there for the catwalk. We put catwalks, 2 new catwalks on the inside of Bay 2. Deck pans are in place for pouring the deck. Then the contractor poured the deck before, this is shown obviously before shifting traffic. Then they shifted traffic over to the middle and removed the deck on the right-hand side in Bay 3. This is after the deck was poured. This is about a year ago, last summer. They had poured the deck. This photo was taken in November of 2024. They had removed the deck in Bay 1 over on the left side. And this photo was taken about 2 months ago. They've still got the bridge in this configuration. Working on the painting now. They've got to paint the bridge, finish up the painting. They've got to do the median barrier and the PPC overlay. And then they'll be all done. So thank you very much for giving us the opportunity to give this presentation. Does anybody have any questions at this point? Yes, sir.
So this bridge was non-redundant, fracture critical originally.
That's correct.
And
Yeah.
tie the bridge together, feel differently about its fracture critical nature. Redundant now.
Yeah, that's a great question. I believe so. Yes. There are analytical modeling techniques that you can utilize to analytically validate exactly, the level of redundancy and those kinds of things. We did not do that in this case, but yes, I believe there's definitely a dramatic, I'll put it this way. Okay. It's not 10 girders. Okay. So, there is less redundancy. Okay. There is some level of degree, right? When we talk about redundancy, I know we either say redundant or non-redundant, right? But it's not that black and white. Okay. So it's less redundant than, a 10 girder system, but it's dramatically better than what we had previously. Okay. And so, I normally try to share this anecdote. But your question reminded me of it. So I'm glad that brought it up. When we were out doing initial investigations, you just had the 2 girder system. These bridges were incredibly flexible. You're out on the catwalk underneath the bridge out at midspan, and you're literally like bouncing up and down. Very, very flexible. Okay. And you're not only bouncing up and down, but you're bouncing sideways a little bit, which is a little unnerving. Okay. When we tied these bridges together, I mean, instantly there was a complete change in how the bridge behaved. That was completely eliminated. All right. Now that didn't mean there weren't some level of vibrations, okay, and live load deflections, but all the bouncing and everything was gone. And so it was significantly reduced and actually even improved as we went on. As you get more, as you lock in the composite behavior with the deck and those kinds of things, there's significant improvement that we observed throughout construction.
This A36 steel on the bridge.
No, it's modified Core 10B steel. I don't remember the number.
That's a higher strength steel, huh?
There's different levels of strength. I think there's some that's 50, 46, 42. Those are the main strength levels from what I remember off the top of my head.
All those awards.
That's a good question. I'm not sure. I don't remember off the top of my head, but I will say this on the floor beams, the new floor beams that we installed, we had more stringent toughness requirements because of limited redundancy there. So we treated those as non-redundant in our design from a material property standpoint. Yes.
So
The final thickness, I think it was 7 1/4. Yeah, 7 1/4, which is less thick than a standard NCDOT deck. We used on the 2 approach spans, we used a standard NCDOT design for the deck there, but then when we got into the 3-span continuous unit, We used lightweight concrete and a thinner deck we kind of optimized the design to minimize the weight on the structure. Yes, sir.
So by minimizing the weight, you are not concerned about the additional down here.
Yeah, so we needed the extra post tensioning on the caps, but from the foundation, we were good. We certainly evaluated that, but you have big spread footings on rock. And so, we analyzed it and did not need to strengthen anything. Yes, sir.
We have a few questions online.
Okay, great.
First one is references made to the state agency involvement. Was there any federal agency involvement?
I don't think so. Tim. This is state funded.
They're all state. Okay.
Yep.
The other question is, can you comment on any significant lane closures?
Yeah, so there were some like nightly lane closures that the contractor utilized, but they were not allowed to have any major long-term lane closures. It's all basically just a nightly closure to help. I think they did it a lot when they were pouring concrete. They could have a little more room. They could have a concrete truck pour up in the lane closure and dump out the concrete, those kinds of things.
Now, I will say, we didn't permanently close lanes, but to be able to keep 2 lanes open, we really had to narrow those lanes on each side. And so it's a little hairy driving through there. But as far as I know, there might have been a few little accidents here and there, but there was never anything that was really serious.
Yeah. Yeah, and I'll just add to that. Every time I went out there, the traffic flowed really well. I was very grateful. I had, you think about as a structural engineer, all the things that could go wrong. I had probably lost more sleep about work zone, traffic control than anything else on this project because of the challenges there. Whenever I talk to the staff, the inspectors on site, they mentioned one time there was an accident pretty far up the hill and they said, man, yeah, it was obvious the guy was driving, whoever it was user error, we'll just say. So, yes, sir.
What do you think the bridge is now?
Yeah, that's a great question. I mean, it's designed for AASHTO. I don't know if 75 years, I don't know if we'll get a full 75 years, but it's certainly got a very, very good, the deck should be a 75-year service life. As long as Tim's successor can paint the bridge every 20 years or something like that, we should get a good long service life out of it. And that's an advantage of steel, right? If you clean and paint, it'll last. Do you have, yes, ma'am.
Now, obviously, it's got more lanes. How far into the road, into the approaches that you have to adjust the roadway to?
Yeah, it was, that was probably a good lesson learned. It was farther than what we had assumed in the feasibility phase, but I don't know, it was maybe a quarter of a mile on each end, something like that. Yes, sir.
Don't have any issues.
Oh, not really. Yeah, not really. This area definitely was hit hard. But this bridge is up so high. You could see devastation and down trees all along the river and things like that. But there were down trees all along the interstate. But other than that, I'm not aware of any other issues.
I think there may have been some issues at maybe some of the shoulders at the approaches, but it wasn't. It was relatively.
Yes, sir.
The original bridge was not painted, is that correct?
That's correct.
You mentioned painting now.
Yeah, we are.
What's the decision there?
Yeah, we are painting near the expansion joints. The original bridge was not painted. It was just purely weathering steel, but we're doing a little extra in that regard for corrosion protection.
But is it just locally there?
Yeah, just locally around the joints. We are painting the exterior girder and along the bottom flange, and we're painting a few key areas where we've got splices, cleaning and painting some of the splice areas. So it's localized though. Yes. Yes.
What's the duration of the design phase?
Yeah, so Tim reached out to me in early 2018. We spent about 6 to 9 months on the feasibility. Design phase was a year or two, year and a half or 2 years, something like that. It went to construction in March of 2021. And they're almost done with construction now. So it's been over 4 years of construction. Yes.
You still have plan to monitor with the staging after the construction?
Yeah, that's a good question. We will not, in fact, our instrumentation team is basically scheduled to go and decommission the instrumentation system in August. So we're getting close to decommissioning that.
John, one last question.
Yeah.
Can you tell everybody again how much money we saved between this option and the full replacement?
Yeah. So about a quarter of the cost is what the rehabilitation option costs from what we estimated to the full replacement alternative.
In dollars?
Yeah, so construction cost was initial cost is 26 million was the bid price. So you're looking at least $100 million to replace these.
You all are taxpayers in North Carolina. Didn't say this would take time. So
Yeah.
when your boss time comes around.